Hello and welcome. In this video, we will explore the differentiation of exponential functions, a key topic in IB mathematics analysis and approaches higher level. By the end of this session, you will be able to differentiate exponential functions of the form b to the power of x, e to the power of x, and a to the power of x, as well as their composite forms using the chain, product, and quotient rules. Let's begin by recalling the properties of the simplest exponential functions. An exponential function has the form f of x equals b to the power of x, where b is a positive constant not equal to 1. The base b determines the function's behavior. Let's look at the graphs of a few examples. Here we see the graphs of several exponential functions. Notice that they all share some common features. First, every graph passes through the point 0, 1. This is because any non-zero number raised to the power of 0 is 1. Second, all graphs are asymptotic to the x-axis at one end. This means they get infinitely close to the x-axis but never touch it. Third, all graphs lie entirely above the x-axis. The range of these functions is all positive real numbers. Now, let's investigate the derivative of these functions. Our goal is to find a general rule for the derivative of b to the power of x. To find the derivative of f of x equals b to the power of x, we will use the first principle's definition of the derivative. The definition states that the derivative f prime of x is the limit as h approaches 0 of f of x plus h minus f of x, all divided by h. Let's substitute our function, f of x equals b to the power of x, into this definition. This gives us the limit as h approaches 0 of b to the power of x plus h minus b to the power of x, all over h. Now we can use the exponent rule that says b to the power of x plus h is equal to b to the power of x times b to the power of h. Applying this rule, our expression becomes the limit as h approaches 0 of b to the power of x times b to the power of h minus b to the power of x all over h. We can now factor out the common term b to the power of x from the numerator. This simplifies to the limit as h approaches 0 of b to the power of x times the quantity b to the power of h minus 1 all over h. Since b to the power of x does not depend on h, we can pull it out of the limit. So the derivative is b to the power of x times the limit as h approaches 0 of b to the power of h minus 1 all over h. Let's analyze this limit. What does it represent? If we look at the definition of the derivative again, this limit is the derivative of f of x equals b to the power of x, evaluated at x equals 0. In other words, the limit is equal to f prime of 0. It represents the gradient of the tangent line to the curve y equals b to the power of x at the point 0, 1. Visually, this limit is the slope of the tangent line at the y-intercept. So, we have found a general formula for the derivative of b to the power of x. The derivative of b to the power of x is equal to the function itself. B to the power of x multiplied by the gradient of the tangent at x equals 0, which we call f prime of 0. This is a remarkable result. It tells us that the derivative of an exponential function is proportional to the function itself. The constant of proportionality is the gradient at x equals 0. This leads to a natural question. Is there a special value of b for which the derivative is exactly equal to the original function? That is, can we find a b such that f prime of x equals f of x? If we can find such a b, it would mean that the gradient of the tangent at any point x is equal to the value of the function at that point. Using our formula, f prime of x equals f prime of 0 times b to the power of x, we can set this equal to f of x, which is b to the power of x. This gives us the equation f prime of 0 times b to the power of x equals b to the power of x. Since b to the power of x is never 0, we can divide both sides by it. This simplifies to f prime of 0 equals 1. So, the special value of b we are looking for is the one where the gradient of the tangent at x equals 0 is exactly 1. Let's recall the definition of f prime of 0. F prime of 0 is the limit as h approaches 0 of b to the power of h minus 1 all over h. We need to find the value of b that makes this limit equal to 1. This is a non-trivial limit to evaluate directly. However, we can use a clever algebraic manipulation. If the limit of b to the power of h minus 1 over h is 1, then the limit of b to the power of h must be equal to the limit of h plus 1. As h approaches 0, The limit of h plus 1 is simply 1. So we have the limit of b to the power of h equals 1. This doesn't help us find b directly. Let's try a different approach. We can rewrite the expression b to the power of h minus 1 over h. Consider the equation b to the power of h minus 1 equals h. This is an approximation for small h. We can rearrange this to solve for b. Adding 1 to both sides gives b to the power of h equals h plus 1. Then raising both sides to the power of 1 over h gives b equals h plus 1 to the power of 1 over h. To find the exact value of b, we need to take the limit as h approaches 0. So b is the limit as h approaches 0 of h plus 1 to the power of 1 over h. This is a famous limit. If we let n equal 1 over h, then as h approaches 0, n approaches infinity. Substituting this into the limit gives us the limit as n approaches, infinity of 1 plus 1 over n, all to the power of n. This limit defines a special irrational number, which we call e. The value of e is approximately 2.71828. It is the unique base for which the derivative of the exponential function is the function itself. Therefore, we have found the most important differentiation rule for exponential functions. If f of x equals e to the power of x, then its derivative, f prime of x, is also e to the power of x. This function is its own derivative. Now that we know the derivative of e to the power of x, let's extend this to composite functions using the chain rule. Our objective is to differentiate functions of the form e to the power of f of x. Consider a function we equals e to the power of f of x. We can think of this as a function of a function. Let's define a new variable, u, to be equal to the exponent f of x. Then our function becomes y equals e to the power of u. The chain rule states that the derivative of y with respect to x is the derivative of y with respect to u, multiplied by the derivative of u with respect to x. So, di dx equals di du times du dx. Let's find each of these derivatives. The derivative of y equals e to the power of u with respect to u is simply e to the power of u. And the derivative of u equals f of x with respect to x is f prime of x. Now we multiply these two derivatives together. This gives us di dx equals e to the power of u times f prime of x. Finally, we substitute back u equals f of x to express the derivative in terms of x. The result is di dx equals e to the power of f of x, multiplied by the derivative of the exponent, f prime of x. This is the chain rule for the exponential function. In simpler terms, to differentiate e to the power of a function, you write the function itself and multiply it by the derivative of its exponent. Let's summarize this rule. The derivative of e to the power of x is e to the power of x. The derivative of e to the power of f of x is e to the power of f of x times f prime of x. Let's work through some examples to see how to apply these rules, including the product and quotient rules. Our first example is y equals 2 times e to the power of x plus e to the power of negative 3x. This is a sum of two terms, so we can differentiate each term separately using the addition rule. The derivative is the derivative of the first term plus the derivative of the second term. For the first term, the derivative of e to the power of x is e to the power of x. The constant 2 remains, so the derivative of 2e to the x is 2e to the x. For the second term, e to the power of negative 3x, we use the chain rule. Here, f of x is negative 3x, so f prime of x is negative 3. The derivative is e to the power of negative 3x, multiplied by the derivative of the exponent, which is negative 3. Combining these, we get our final answer. The derivative di dx is 2e to the x minus 3e to the negative 3x. Let's try an example that requires the product rule. Consider the function y equals x squared times e to the power of negative x. This is a product of two functions, u equals x squared and v equals e to the power of negative x. The product rule states that the derivative is u prime v plus u v prime. First, let's find the derivatives of u and v. The derivative of u equals x squared is u prime equals 2x. The derivative of v equals e to the power of negative x is v prime equals negative e to the power of negative x using the chain rule. Now we substitute these into the product rule formula. This gives us di dx equals 2x times e to the power of negative x, plus x squared times negative e to the power of negative x. We can simplify this expression by factoring out the common term e to the power of negative x. The final simplified derivative is diex equals e to the power of negative x times the quantity 2x minus x squared. Next, let's tackle an example using the quotient rule. Let's find the derivative of y equals e to the power of 2x divided by x. Here, the numerator is u equals e to the power of 2x, and the denominator is v equals x. The quotient rule states that the derivative is u prime v minus uv prime, all divided by v squared. Let's find the derivatives of u and v. The derivative of u equals e to the power of 2x is u prime equals 2e to the power of 2x using the chain rule. The derivative of v equals x is v prime equals 1. Now we substitute these into the quotient rule formula. This gives us dx equals 2e to the power of 2x times x minus ie to the power of 2x times 1 all divided by x squared. We can simplify the numerator by factoring out e to the power of 2x. The final simplified derivative is dx equals e to the power of 2x times the quantity 2x minus 1, all divided by x squared. Let's look at another chain rule example, this time with a power function. Find the gradient function for y equals the quantity e to the power of x minus 1, all cubed. This is a composite function. The outer function is a cubic, and the inner function is e to the power of x minus 1. Let's define u equals e to the power of x minus 1, then y equals u cubed. Using the chain rule, di dx equals di du times du dx. The derivative of y equals u cubed with respect to u is 3u squared. The derivative of u equals e to the power of x minus 1 with respect to x is e to the power of x. Multiplying these together gives us 3u squared times e to the power of x. Substituting back u equals e to the power of x minus 1, we get the final answer. di dx equals 3 times e to the power of x minus 1 squared times e to the power of x. Now let's consider the derivative of a general exponential function, a to the power of x, where a is any positive constant. Our objective is to find a rule for the derivative of y equals a to the power of x. The key to differentiating a to the power of x is to rewrite it using the natural exponential e. We can use the property that a equals e to the power of the natural logarithm of a. So we can write a to the power of x as e to the power of the natural logarithm of a, all raised to the power of x. Using the exponent rule that says x to the power of m to the power of n equals x to the power of m times n, we can simplify this. This becomes y equals e to the power of x times the natural logarithm of a. Now we have a function in the form e to the power of f of x, which we know how to differentiate using the chain rule. Here the exponent f of x is x times the natural logarithm of a. Since a is a constant, ln a is also a constant. The derivative of f of x is simply the constant ln a. Applying the chain rule, d dx is e to the power of x ln a, multiplied by the derivative of the exponent ln a. Finally, we substitute back e to the power of x ln a with its original form, a to the power of x. This gives us the final rule. The derivative of a to the power of x is a to the power of x multiplied by the natural logarithm of a. This rule makes intuitive sense. Remember that the derivative of b to the power of x was b to the power of x times f, prime of 0. For the base e, f, prime of 0 was 1. For any other base a, fe prime of 0 is ln a. Just as we did with e to the power of f of x, we can extend this rule to composite functions of the form a to the power of f of x. Suppose I equals a to the power of f of x. We can use the chain rule again. Let u equal f of ni, then y equals a to the power of u. The chain rule gives us dID equals di du times du de. The derivative of y equals a to the power of u with respect to u is a to the power of u times ln a. The derivative of u equals f of x with respect to x is f prime of x. Multiplying these together gives us a to the power of u times ln a times f prime of x. Substituting back u equals f of x, we get the final rule. The derivative of a to the power of f of x is a to the power of f of x times the natural logarithm of a times the derivative of the exponent ef prime of x. Let's see this in action with an example. Find the derivative of y equals 5 to the power of x squared minus x. Here, the base a is 5, and the exponent f of x is x squared minus x. The derivative of the exponent f prime of x is 2x minus 1. Now we apply the formula. The derivative di dx is 5 to the power of x squared minus x times the natural logarithm of 5 times the quantity 2x minus 1. Let's work through a more complex problem that combines several of these concepts. The tangent to the function f of x equals x squared times e to the power of negative x at point P is horizontal. Find the possible coordinates of P. A horizontal tangent line has a gradient of 0. So our task is to find the x values where the derivative f prime of x is equal to 0. First, we need to find the derivative of f of x. This is the same function we differentiated in example 2, so we already know the result. The derivative is f prime of x equals e to the power of negative x times the quantity 2x minus x squared. Now we set the derivative equal to 0 and solve for x. We need to solve the equation e to the power of negative x times the quantity 2x minus x squared equals 0. The product of two terms is 0 if and only if at least one of the terms is 0. Let's analyze each term. The term e to the power of negative x is an exponential function, which is always positive and never equals 0. So this term cannot be 0. Therefore, the other term must be 0. We must have 2x minus x squared equals 0. We can factor out an x from this expression. This gives us two possible solutions for x. Either x equals 0 or 2 minus x equals 0, which means x equals 2. These are the x-coordinates of the points where the tangent is horizontal. To find the full coordinates of P, we need to find the corresponding y values by plugging these x values back into the original function, f of x. For x equals 0, f of 0 is 0 squared times e to the power of 0, which is 0 times 1, or 0. So one possible point is 0, 0. For x equals 2, f of 2 is 2 squared times e to the power of negative 2, which is 4e to the power of negative 2. So the other possible point is 2, 4e to the power of negative 2. So there are 2 points on the curve where the tangent line is horizontal. The origin, 0, 0, 0, and the point, 2, 4e to the power of negative 2. Let's recap what we've learned today. We started by investigating the derivative of b to the power of x and found that it is proportional to the function itself. We then discovered the special number e, approximately 2.718, which is the unique base for which the derivative of the exponential function is the function itself. We extended this to composite functions using the chain rule, and we saw how to apply the product and quotient rules to functions involving exponentials. You are now equipped to differentiate a wide variety of exponential functions. To solidify your understanding, here are 5 practice questions in the style of IB assessment. Pause the video, work through them, and then check your solutions. Question 1. Differentiate e equals 3 times e to the power of 4x minus 2 times e to the power of negative x. Question 2. Find the derivative of f of x equals x cubed times 2 to the power of x. Question 3. Find the gradient of the tangent to y equals 1 over the square root of e to the power of 2x plus 2 at x equals 0. Question 4. The tangent to f of x equals 2 to the power of x plus 4 to the power of x at point P has gradient ln2. Find the coordinates of P. Question 5. Given the function f of x equals e to the power of kx plus x and f prime of 0 equals negative 8, find the value of the constant k. Welcome back. Let's go through the solutions to the practice questions. For question 1, we differentiate term by term. The derivative of 3e to the 4x is 3 times e to the 4x times 4, which is 12.5e to the 4a. The derivative of negative 2e to the negative x is negative 2 times e to the negative x times negative 1, which is 2e to the negative x. The final answer is 12e to the 4x plus 2e to the negative x. For question 2, we use the product rule. Let u equals x cubed and v equals 2 to the x. Their derivatives are u prime equals 3x squared and v prime equals 2 to the x times ln 2. Applying the product rule gives 3x squared times 2 to the x, plus x cubed times 2 to the x times ln 2. Factoring out x squared times 2 to the x gives the simplified answer. For question 3, we first rewrite the function as y equals e to the 2x plus 2, all to the power of negative 1/2. Then we use the chain rule. The derivative is negative 1/2 times the inner function to the power of negative 3/2, times the derivative of the inner function, which is 2e to the 2x. Simplifying gives negative e to the 2x times e to the 2x plus 2 to the power of negative 3/2. Plugging in x equals 0 gives a gradient of negative 1 over 3 root 3. For question 4, we find the derivative of f of x, which is 2 to the x ln 2 plus 4 to the x ln 4. We set this equal to the given gradient, 2. We can rewrite ln 4 as 2 ln 2. Dividing by ln 2 gives 2 to the x plus 2 times 4 to the x equals 1. Since 4 to the x is 2 to the 2x, we have 2 to the x plus 2 times 2 to the 2x equals 1. Let u equals 2 to the x. This gives the quadratic equation 2u squared plus u minus 1 equals 0. Solving for u gives u equals 1/2 or u equals negative 1. Since u equals 2 to the x must be positive, we take u equals 1/2. So 2 to the x equals 1/2, which means x equals negative 1. The y-coordinate is f of negative 1, which is 3, 4. The coordinates of p are 1, 3, 4. For question 5, we find the derivative of f of x, which is k times e to the kx plus 1. We are given that f prime of 0 equals negative 8. Plugging in x equals 0 gives k times e to the 0 plus 1 equals negative 8. Since e to the 0 is 1, we have k plus 1 equals negative a. Solving for k gives k equals negative 9. I hope this video has provided a clear and rigorous explanation of how to differentiate exponential functions. Thank you for watching.